Yeah, we're up and running. Set that aside over there. Yeah, I can see everything. Okay. So this is the topics for today coming out of your textbook are from chapter 6. That means that chapter 4, 5, and 6 will have been covered after today's meeting. And those will be the chapters that will be covered in the second exam. Next Friday, we'll have a review on all three of those chapters. And then I believe we have a spring break, if I'm not mistaken. Let me get my bearings again. Yes, we'll have a review on the 12th, and then we'll have spring break. So you have all that time to prepare for the exam that will be due on March 26th. And on that day, we'll also jump into new material. Okay. So let's get on the road with this chapter 6. Up to this point, we've learned how to do calculations. We've learned how to write compounds and name them. And now we're going to extend those skills to calculations involving tracking how much reactants go into a reaction and how much products come out. So that's our end game. Let's see. There we go. So we need some way of accounting for things that are going on at the microscopic level. We can't see them, but we infer from various laws and theories what we think is actually happening. And so, for instance, when we talk about elements and compounds, we know how to write them, but we need to know how much of those substances are actually there while we're discussing them. And one of the ways to approach that is how much does each atom weigh? How much does each compound weigh? And that's what the atomic mass, the atomic mass unit references. So one atomic mass unit is roughly equivalent to the mass of a proton. It's not exact because we reference everything to some standard. And the standard happens to be carbon. Okay, that particular isotope of carbon with 6 protons and 6 neutrons, making 12, that is arbitrarily given the mass of 12 atomic mass units. However many significant figures you need. That's the standard. And everything else is compared to that. So what that means is, for something like oxygen, if we have an oxygen isotope of, say, 8 protons and 8 neutrons, we'd have a mass of 16. But it's not exactly 16. Now, the my mind's gone blank, I'm sorry. This number right here. We take that and we define that as the sum of protons and neutrons. So when you put that number up there next to a symbol, that's what it means. But when we define the actual mass of the atom, for oxygen, it won't be exactly 16 because there's some variability in measurement, and there's some variability in the construction of the atom that says that it's not exactly 16. So carbon 12 is the only one that is exactly 12 atomic mass units. Okay, so if we know atomic mass units, and of course, there's the issue of average atomic mass. Right? If you have that, and you have that, the distribution of this isotope and that isotope and that isotope of carbon, then the average atomic mass won't be exactly 12 either. In fact, the average for these will be 12.01 to two decimal places. Okay, so that's what you're looking at when you look at the periodic table and you see the atomic mass in, well, on this table it's in the upper left-hand corner of each of the little squares. It's a weighted average. So we can say for each element what the atomic mass units are. And then when we discuss compounds, such as this example here, 10,2-fluoride, right? That compound can be calculated atomic mass based on the values for each of the elements. So in this case, you have 118.71 for the 10 and 2 times 19 for the fluorines. So the total then is 156.71 atomic mass units for that molecule. Actually, that's not a molecule because it's a metal and a non-metal. Right? Molecules are specific to non-metal nonmetals. This would form some type of crystal lattice. But this is the simplest ratio of 10 to fluorine. Okay, just like sodium chloride would be, the simplest ratio would be 1 to 1. So that's how we calculate the mass for a compound. You just add up the individual atoms. Okay, so for H2SO4, you would add up 2 hydrogens, right? And 1 sulfur. I have to look that up. I think it's 3307. And 4 oxygens. Okay, add those all together, and you get 98. Actually, you get 98. Let's see. Hold on a second. .09, actually. Right? Yeah. Oh, 99. That's not right. Let me try that again. Okay. Oh, that's wrong. 32. Okay, what am I doing wrong? Yeah, 9809. Okay, so how did they get 98 out of that? What they did was they took the most common isotope, right? For this one would be 1 for hydrogens. For this one would be 32. And for this one, 16. So that's why they get 98, because they were taking the most common isotopes. If you do this with the average atomic mass, you would get 9809. Okay? So that's how you would express mass for a compound in atomic mass units. But atomic mass units aren't very useful for chemists. We need something we can measure. And in order to do that, you need lots of atoms, lots of molecules to give you enough mass that you can measure on a balance. So we have a unit of measure called the mole. And it's just a number of things, right? You could have a mole of atoms, a mole of molecules, a mole of formula units, which would be those for metal, non-metal combinations like sodium chloride, tin 2 fluoride, and those things that don't form discrete molecules like water, carbon dioxide, and those. And those molecules are covalently bound, so they're very strong within the molecule, and then their interactions with other molecules are independent. Whereas with metals, non-metals, you have a crystal lattice where you have lots of ion interactions. So back to the topic. Atoms, molecules, formula units. You could have a mole of chickens for all I care. It's just a number. But it's also an experimentally determined number. Right? And it means that if you have 12 grams of carbon 12, you have 1 mole of atoms. And that mole has been measured to be 6.022 times 10 to the 23rd atoms. Okay? Now, that number is constantly being refined, but for our purposes, to 3 decimal places, it will not vary. It changes way out here with these smaller decimal units. And that's important for some scientists in their work, but for us, it's not. 6.022 times 10 to the 23rd will stay that way and never change. Okay. So by saying this many atoms is equal to that 1 mole, we have a conversion factor. Remember, every conversion factor is derived from an equivalence. So if 1 mole equals that many atoms, then if you know how many moles of a substance you have, say 3 moles, 3 moles of atoms, then you can convert to the number of atoms. Right? So just 3 times that. So it'd be 1.8066 times 10 to the 24th atoms. Okay? It's a conversion factor. So if we would do that with eggs, say a mole of eggs, of course you wouldn't have 12 eggs, right? That's just ridiculous. I mean, it's too small. So you would say, all right, so if you have a mole of eggs, then you have 6.02 times 10 to the 23rd eggs. Okay? So now we have an expression called molar mass. And this is where we start to get values that are useful. What we're saying is, if we have a mole of atoms, or a mole of molecules, or a mole of formula units, it will weigh so many grams. How many grams is that? Well, as it turns out, the number of grams of an atom, if you have a mole of them, is equal to that atomic mass unit number. So in this case, for nitrogen, you find that the average atomic mass is 14.01 atomic mass units for nitrogen. You just look it up on the periodic table. That number is also equal to the number of grams if you have a mole of those atoms. Okay, so that number in the periodic table has two meanings. You attach the units depending on which one you need, and most of the time we need grams per mole. Carbon dioxide, you just take the value for carbon and 2 times the value for oxygen, add them together, and now we know that carbon dioxide, its molar mass is 44.01 grams per mole. Okay, so I already told you that. As long as you have an equivalence, you've got a conversion factor. So it could be 14 grams per mole, or it could be 1 mole per 14 grams, right? Conversion factors, remember, are always equal to 1. So the inverse is identical. Either way, it doesn't matter. It's still equal to 1. Okay, so calculate the mass in grams of 2.5 moles of ethane. So we are given 2.5 moles, and we want to convert to what? What's the mass in grams? Got another attendee here. Let's see. Okay, there we go. Got you checked in. In other words, we would need a conversion factor that would give us grams, right? So grams goes on top, moles goes on bottom. And whenever you see grams and moles in a quotient like that, whether grams is on the top or on the bottom, it doesn't matter. Always think molar mass. And we need the molar mass of C2H6. So we need 2 times 12.01 and 6 times 1.01. Right? And that will be grams per mole. All right. So we end up with 30.07 grams in 1 mole. Moles cancel. 2.5 times 30.0 is roughly 75 grams. So if we have that many moles of ethane, we also know that we have this many grams of ethane. This goes back to what I was saying very early on. There's so many problems in chemistry that can be solved simply with dimensional analysis, right? Conversion factors. Now, they mean something different for each one that you use, but the skills required for using conversion factors don't change. You're still starting off with one unit, ending up with a different unit, and you need a factor in between to make the conversion, right? In this case, we're converting moles into mass. But you could turn it around and say, well, I want to convert those. Say, I know I have this many grams of ethane. I want to know how many moles it is. And you just reverse the process. So the number of moles of 50 grams of water, we just calculate 2 hydrogens and 1 oxygen, 18.02 grams. Now in this case, grams is on the bottom and the moles on the top, because moles is our destination. Grams cancel, leaves you with the, well, actually this is the thinking part. The rest is number crunching. 18.02 divided into 50 gives you 2.78 moles of water. Okay, you're probably wondering why we need to know this. I'll give you a hint. We're on the way to using balanced equations to determine how many grams of product, for instance, that you will expect from the reaction of so many grams of each of your reactants. Right? The thing about it is, and I'll say this again when we get to that point, you can't go directly from grams of reactants to grams of products. It doesn't work that way. Reactions are atoms and molecules, numbers of those reacting together. The grams are just baggage. They come along for the ride. Okay, we'll get back to that in a second. So here's the molecular formula for aspirin, C9H8O4. A lot of people don't take aspirin anymore. Well, yeah, they do. They don't take it for pain relief so much as they do Tylenol and Advil and maybe Naproxen, things like that. Aspirin is not quite as popular as it once was because we have these other substitutes. But people like me take a baby aspirin every day just to keep your blood from clotting in your veins. So this compound has that formula. You have 9 carbons, 8 hydrogens, and 4 oxygens. So what is the mass of 1 mole of aspirin? You just add them up. 9 times 12.01, 8 times 1.01, and 4 times 16. Add those all together, and you end up with 180 grams. Okay? So now we know that 1 mole of aspirin weighs that much. There probably should be a period here to preserve that 0 as a significant figure. Just saying. Okay. So the chemical formula that we know how to write and how to, well, we know how to write the formula, has subscripts. And those subscripts are there for a reason, because they say this is how many atoms of that element are present in this formula unit. Now, once you write that, that is sacred cow. You can't touch it, because if you do, you have a different compound. So we say this is dinitrogen tetroxide, 2 atoms of nitrogen and 4 atoms of oxygen. And the question is, in one formula unit, how many atomic mass units do you have? Right? Well, it's not going to answer that question, is it? That's one formula unit. So we just say 2 times 14.01 and 4 times 16 and add them together. And that would be the atomic mass units for that molecule. But that's also the number of grams of dinitrogen tetroxide that you would have if you also had 1 mole of those molecules. And that would be the macroscopic view. It's something that we can hold, right? There's enough of them now that we can measure them on a balance. Okay, so when we look at a formula like this, how many moles of carbon atoms and how many moles of hydrogen are present? Well, if you only have 1 mole, then you know that 2 moles of carbon are present and 6 moles of hydrogen in that 1 mole of ethane molecules. But if you have 2.5 moles of that sample, you have 2.5 times that much. Right? So you would have 2 times 2.5 would be 5 moles of carbon. Or 6 times 2.5 would be 15 moles of hydrogen atoms. Okay? So how many moles of carbon atoms do you have in this one? 9, right? And 8 hydrogens and 4 oxygens. It's not complicated. You just have to keep in your mind, what are we talking about? Well, if we're talking about moles, then 1 mole of this compound is composed of 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. All right, this is the author's idea in your book of a useful flow chart. And if you find it useful, that's fine. I prefer conversion factor approach. Then I don't have to memorize all this stuff. I just say, where am I? Where am I headed? How do I get there? So in this case, we're given certain information. We know what our target is. Excuse me. And we need a conversion factor to get there, or multiple conversion factors, as the case may be. All right. So just as a side problem to see if you understand how to get from one place to the other, if we have this question, how much money do I need to carry with me to get from Beckley, West Virginia to Atlanta, Georgia? And that's a trip I used to make quite often because I have family down there. So what do you need to know? Well, what's the target? The target is money. How much money do I need? Right? What's the given information? How far am I traveling? How many miles? Right? So given is 385 miles, roughly. Atlanta's a big place, so if you're going to the near side, it'd be less. If you're going to the far side, it'll be a lot more. So what's the target? Dollars. Right? So how do you get there? Well, we need a factor that'll convert miles into dollars. I don't have a single factor, right? That'll go from miles to dollars. We don't know how many miles per dollars there is in that calculation, but we do know the price of gasoline, because that's what you need to buy to get there, right? So it's so many dollars per gallon, right? So that leads you to the conclusion that how many gallons of gasoline are you going to need? Well, it depends on your car. What's the mileage of your car? Like 20 miles per gallon, 25 miles per gallon, 30 in some cases, or more. So I just picked something. I said, okay, let's say my car's tuned, it's running great. I don't make a lot of short stops on the way down there. 25 miles a gallon is a good round number. So what does that give us? That says this is how many gallons I need. And then we need to convert gallons to dollars. So there's my other factor, right? And it turns out that for a one-way trip with that price of gasoline and that efficiency of my car, I need $43.12 to get there. Now, if I want to come back, I also need $43 to come back. And if I want to drive around a little bit when I land there, I need some buffer. So I usually add about 10% or more to that. So that'd be 86 plus 94. Let's just round it off to $100. So I keep $100 in the glove compartment that I don't touch for anything else but gas, or it's on a card or something like that. So that's how this is a practical problem that we've solved with dimensional analysis, conversion factors. Now back to chemistry. So which of the following of these would be closest to the average mass of one atom of copper in grams? All right. None of these A, B, C, D, those are not reasonable. I mean, who would believe that one atom of copper weighs 60 grams? Right? If you have any intuition at all about what a gram weighs, one copper atom can't be that much. So if you're in a hurry on a test, this is the only possible answer. But how do we get that value? Well, we're starting out with one atom. Let's see. No, that's not. We're starting out. I'm going to have to do this one on the board. We're starting out with one atom. That's given. Of copper. And we want to end up with grams. There's nothing that'll get us directly there. We don't know how much. Well, there is a factor, but we don't know what that is for copper. You know, how much does a copper atom weigh? But we do know how much a mole of copper atoms weighs. So how many moles is that? Okay, so now we've got moles. Now we can go to our periodic table and find that actually this is the molar mass of copper, 63.55. So 1 mole weighs 63.55 grams. So multiply that times 1 divided by this, and you get 1 times 10 to the minus 22nd grams per atom. That's how we arrived at that number. Okay. This is just a reality check. I mean, do you really understand what we mean by molar mass? Calculate the number of copper atoms in a 63.55 gram sample of copper. If that's the molar mass, that means we've got 1 mole of atoms. How many do we have? 1 mole is 6.022 times 10 to the 23rd atoms. So that's the answer. You have 1 mole if you have that many grams. And that's how many copper atoms you have. Okay. All right. So let's do a little comparison shopping here. If we have 100 grams each of these metals, magnesium, zinc, and silver, 100 grams, 0.0. All right. Which gives us the greatest number of atoms? All right, we could go through the process of calculating the number of atoms, right? If you got time to do that, that's fine. It's good practice. But if you're in a hurry on a test, you want to get the answer and move on. So understand that if we have equal masses of each one does not weigh the same amount per atom, right? So what's the molar mass of magnesium? Well, magnesium is 24.31. Zinc is 65.38. And silver is 107.87. Okay? So, which one would give you the greatest number of atoms? The lightest one, the one that weighs the least amount, right? This is also atomic mass units. So that atom weighs this much in atomic mass units. This one weighs that. So the heaviest one would require the fewest number of atoms to give you that mass. Okay. So we could go ahead and do the calculation, but I think if we divide that into that, you get a certain number, that and that, and that, and that. So this one is the greatest number. The lightest atom requires the most numbers of atoms to give you the same mass as some other, right? So magnesium is the one that weighs the least per atom, requires the most atoms. And this derives directly from Avogadro's law when he compared gases. Remember that? That was the problem that chemists were having. Well, in Europe, that's where the meeting took place. Chemists were having this problem because they only understood mass. Reactants go in, products come out. And they knew that the mass going in is equal to the mass coming out. But they didn't know what happened in between. They didn't realize that it wasn't mass that was interacting in the reaction. It was atoms and molecules, numbers, right? So Avogadro solved that problem for them, well, by way of a student of his, Cannizzaro. Remember, he said that if you have two gases and the volumes are equal and the temperatures are equal and the pressures are equal, then the number of molecules in each of these containers is equal. Right? If you know that the number of molecules in each one are equal, then if this one weighs more than that one, that means that each individual molecule or atom in this one weighs more than that one. So now they were able to relate masses for individual atoms and molecules by that, simply by that law. And now, of course, over the decades, we've refined it to the point where we actually have measured values that we can work on. We don't have to go through the process of using gases and so forth. We have a periodic table that's fairly complete now. In fact, all 118 elements in the current table have names. Okay. Rank the following according to their descending number of atoms. So greatest, next, least. All right. Notice we have different values here. Okay. So we're going to have to do some comparison here with actual calculations of numbers of atoms. But it's not that difficult, because if we're comparing numbers of atoms, we can just stop at moles, because moles is a measure of numbers, right? We don't have to calculate the number of atoms. We can just stop at moles and do the comparison. It'll be the same thing as comparing the numbers of atoms. So for 107.9 grams of silver, okay, compared with 70 grams of zinc and 21 grams of magnesium. Okay, since we're just putting these in order, really all we need to know is which one's the greatest, which one's the least, and the other one's in the middle. Okay, so how do we find out how many atoms we have, how many moles there are? We need the molar mass, right? So what's the molar mass of silver? 107.9. So that's equal to 1 mole, right? 107.9 grams is 1 mole. How about this one? What's the molar mass of zinc? Well, let's see, zinc is 65.38. That's greater than a mole, is it not? How about 21 grams of magnesium? It's 24.3 molar mass. So that's less than a mole. Okay, now we can put them in order. What's the greatest? This one is greater than a mole. So it's zinc is greater than, and the least is this one, and silver's in the middle. right? So we solved that problem in 20 seconds. Okay, I actually did the calculations here just for the hell of it. But that's all you need to solve the problem, just to recognize, since you've only got 3 of them, you just need to know their relationship to moles. As it turns out, since silver is equal to 1 mole, then all you had to do is find out greater than or less than for the rest of them. Okay, so if we have 100-gram samples each of the following: water, dinitrogen monoxide, which is nitrous oxide, laughing gas. This looks to be propionic acid, okay? And there's carbon dioxide. Rank them in descending order of number of oxygen atoms. This requires a little bit more work. I think I've got this. Let me check my hard copy. I think I've got this worked out on the slide, so I don't have to put it on the board, and we can save some time so that we don't run out of time. Yeah, okay. So we need to invoke Henry Ford, right? Assembly line. We're going to do the same calculation for each one, just changing the factors as required, and then compare the number of oxygen atoms, right? So here we go. We've got water, dinitrogen monoxide, propionic acid, and carbon dioxide. So there's 100 grams of water. We need to convert to moles of water molecules. That's what 18 grams does. It says now we have this many moles with those 2 factors, this many moles of water. What's the ratio of oxygen to water? It's 1 to 1. 1 mole of oxygen for every mole of water. You can see that from the formula. There's 1 here for the whole. So that's your conversion factor to get rid of water and leave you with moles of oxygen. So the calculation gives us this many moles of oxygen. We repeat that process for nitrous oxide, right? There we convert to moles of nitrous oxide, and here we take the ratio of oxygen to nitrous oxide to finish the calculation. How about this one? This one's going to be a calculation for moles of propionic acid, but now the ratio is 2 moles of oxygen for every 1 mole of the molecule. So that gives us this value for moles of oxygen. And similarly, carbon dioxide. Okay, so in descending order, we would have of oxygen atoms, right? We don't have to convert to atoms, right? Mole is a measure of numbers of atoms or numbers of molecules or whatever your case may be. So the most is water. Next is carbon dioxide. Next is propionic acid. And last is nitrous oxide. Okay? So that took a little longer than 20 seconds, maybe 1.5 minutes to 2 minutes, if you know what you're doing. Okay, so here's the formula of aspirin again, right? What does that look like? Anybody know what aspirin looks like? The formula looks like? Right? It's a ring structure. That's central, like the benzene ring, right? And then you have, there's the acid, right? That's a carboxylic acid group. And then salicylic acid would have this. It's like that, a hydroxyl on the side. But aspirin is acetyl salicylic acid. So we take this one, and then we go, let's see, here, 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 right? So let's see if that adds up. 9 carbons. Let's see, 1, 2, each one of these is a carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. 8 hydrogens. All right, each one of these has a hydrogen. 1, 2, 3, 4, 5, 6, 7, 8. And then 4 oxygens. 1, 2, 3, 4. Okay, so that's it. That's aspirin. Let's say we have a 0.325 gram tablet, right? 325 milligrams. That is the standard for aspirin when used to relieve pain. Right? It's a lot less than that for baby aspirin. I'm trying to remember. It's at 83 something milligrams. But this is what we used to take for pain, right? That's all there was before Tylenol, before Advil. And that, in fact, is equal to 5 grains. That's another measurement of weight, of mass. Anybody in here who loads their own ammunition knows grains, right? But that value of milligrams is equal to 5 grains. Okay, so let's say the question is calculate the number of molecules. All right, so if we need to know the exact number of molecules, you need to just carry it on out. Right, so if you have this many grams, then you need to know the molar mass of aspirin. You do 9 times 12.01 plus 8 times 1.01 plus 4 times 16. And that gives you 180.2 grams per mole. Arranged in the proper position, numerator, denominator, you can cancel the grams, leave you with moles. Then you can convert moles to molecules with this factor. Okay? Okay. Now that we know how to convert grams to moles and moles to grams, we can balance equations. We can set up a chemical reaction in the form of an equation, and we can use that equation to describe the reaction and actually to derive information and do calculations based on that reaction. So the convention is the reactants always go on the left with a plus sign between them. And you have to write the compounds and the elements correctly. That's first. So calcium sulfide is correct. 2 plus for calcium, 2 minus for sulfur. There's 1 to 1. Water is H2O. Right? Now, after you write those and put them in your equation, you cannot touch the subscripts. There's 1 here, 2 there, and 1 there. That is sacred information. You do not touch that at all. I'll tell you what to do later. Calcium oxide is correctly written, 2 plus, 2 minus. H2S, hydrogen sulfide, or dihydrogen sulfide, is 2 pluses and a 2 minus. Okay, now this is, you're given that actually. These are the reactants, these are the products. There are rare occasions where you are able to deduce the products from the given reactants. In a couple of instances. Most of the time, these have to be experimentally determined. You know what the reactants are because you put them there. And then you determine what the products are experimentally. Okay. So now we have to recognize that in order for Lavoisier's law of conservation of mass, we have to have the same number of atoms of each element on both sides of the equation. That also matches with Dalton's atomic theory, in which he said that these, you don't change the number of atoms from reactants to products, you just rearrange them. Right? That was Dalton's contribution. So we have 1 calcium here and 1 calcium there. That's good. We have 1 sulfur here and we have 1 sulfur there. That's good. We have 2 hydrogens here and 2 hydrogens there. That's good. We have 1 oxygen here and 1 oxygen here. That's good. That's great. The equation is already balanced. Same numbers of elements on both sides. Okay? If that were not the case, then you'd need to go through a procedure to balance the equation without touching the subscripts. And we're going to do that. We use prefix numbers for each of the compounds. Those are called coefficients. Those go in front of each of the compounds. Now remember, if the compound is written there and there's no number out here, there's understood to be one, right? If you write the compound, there has to be at least one of them. So we don't write the one. We only write anything greater than one. So for instance, if the question on an exam says, after balancing the equation, add up, sum the coefficients, what is that value? In this case, it'd be 1 plus 1 plus 1 plus 1 equals 4. Okay, don't let that fool you. Or if you had different numbers in here, like 2, 3, and 2, don't forget to add that 1. Okay. The coefficients simply mean that you have one or more units, molecules or formula units of the compound. Okay, that's what that means. It doesn't say anything directly about mass. Now, it does affect the mass once you understand, once you are given an amount. But the coefficients for a balanced equation actually do not affect the mass of the reactants that are given in the problem. In other words, if we write an equation and say, all right, you have so many grams of reactant A and so many grams of reactant B, that has nothing to do with the coefficients. That's just what you have right there in your hands, your gloved hands, or the container in your hands. What they do tell us, those coefficients, is the ratio of the reactants and products in terms of moles. Okay, so say we had A reacting with B, yielding C and D, right? And we had one of these and two of these and three of those and five of those. That's the molar ratio of each of these compounds or elements, as the case may be. So the ratio of this one to that one is 1A for each two B's. Okay? 1 equals 2. I should have put it this way. 1A equals 2 B's. We derive a conversion factor from that. 1A per 2 B's. Or we could say, if we say that 2B is equal to 3C, then we have a conversion factor that could be 2 B's per 3 C's or 3 C's per 2 B's. Right? So you can, from the balanced equation, you can get conversion factors from that balanced equation. And I'm going to show you how those are used in just a minute. Okay, how do we balance an equation? After you've written the unbalanced equation with compounds, elements as reactants and products, then you have to start someplace. Right? You have to pick one. If you find out that one is not equal to the other on reactant product side, then you have to start somewhere, and you introduce a coefficient to make those two elements equal. Well, what that usually does, especially if it's a compound, it changes the numbers of other elements also. Right? And I'll show you how that works in a minute. The reason I put these slides up here is because this is the way the authors express it, so that this will look like something you've seen in the book. But I'm going to give you a better way. You continue with a second, a third, a fourth element, however many it takes, and then you check at the end. Do a count. to see, do you have balanced numbers of each element on both sides? Right? So that's the overall plan. This is just a reminder, right? Balance the number of atoms. Don't touch the subscripts. And the coefficients here should always be the smallest whole numbers that are possible. So if we had 2, 4, 2, and 2, it would be simpler to say 1, 2, 1, and 1. Right? Keep it the simplest whole number ratio for your coefficients. And when that rule changes later on, I'll let you know. But for now, always simplest whole number ratio for coefficients. Okay, so you have to know what the reactants are, what the products are, and sometimes it's important to put the physical states in there. So if you have something like carbon dioxide, more than likely it's gas. Now, if you get it cold enough and compress it, you could get a solid like dry ice, in which case you would say this. They're the same compounds, but they're different physical states, gas versus solid, or it could be a liquid, like that. Or if you open a bottle of pop, you know that it could also be carbon dioxide in aqueous solution, where you're dissolving carbon dioxide gas in the drink. So these are the common ones we're going to use: solid, liquid, gas, aqueous. Those are the suffixes that would go with the compounds. You don't always have to have them. If you're just balancing the equation for numbers of atoms, then that doesn't matter. But when we start using balanced equations and we need to determine masses, for gases we might want to know volume, for aqueous solutions we may want to know concentration, then those suffixes are important. Now, most chemistry books that I've seen say, then you balance the equation by inspection, which is a worthless, meaningless statement, because by inspection could mean anything. I think it's the author's cop-out. They don't want to deal with the mechanics of balancing an equation, so they just say, you're on your own. Well, I'm going to give you a method. And it involves some helpful hints, right? I've listed them here just so that you'd have them in black and white. And we're going to actually balance an equation and use some of these hints to help shorten the process, make it more logical. Now, this procedure that your introduction to balancing equations is going to be in the form of the simplest molecular type structures that you balance. There are other methods for balancing equations that take advantage of what type of equation it is. For instance, if in the reaction electrons are being transferred, like sodium and chlorine gas react, well, you know that electrons are going to go from the sodium to the chlorine to make ions, and then they attract one another, right? That's an ionic bond. But there are some more complicated reactions that can be simplified and made easier by dealing with those transferred electrons first and then finishing with atoms. Right? So that's just a hint as to there are other ways to balance equations, but for now we're going to get started with just the atoms and molecules. Okay, I set up a table. It's on the next page, and what I do is I write the equation and then I set up a table so that I can tally the numbers of atoms on either side. right, in a group. That'll become obvious here in a second. If your formulas contain polyatomic ions on both sides of the equation, and they remain intact, reactants and products. In other words, we don't take the polyatomic ion and bust it up. If you do that, then you can't use this hint. But if the polyatomics are the same on both sides, you can use those as balancing units. Okay, and it shortens and makes more efficient the process. If an element occurs in only one place, right, like here, oxygen on this side, then leave that one till last. Don't put any coefficients here until the very end, for good reason. Because when you put a coefficient here, it only changes that element. It doesn't have any effect on the other elements, like 6 carbon dioxide. That's 6 carbons and 12 oxygens, right, that you have to account for in your budget. And that's what that table I call is my budget. As a corollary to that, hold water, if it's there, next to last. Sometimes you can't do that, but if you can, hold it. Now, we don't want the final equation to have any fractions in it, right? We want whole numbers only. But sometimes we can use a fraction as a coefficient as an intermediate step. And that makes the balancing process easier and quicker. When we put the fraction in, it balances the equation. But then we have to get rid of the fraction. Okay, and I'll show you how to do that too. Okay, I'm going to show you right now. Say in the process of balancing this equation, we had to put a fraction in front of the oxygens, right, as our last step. So 25 halves of O2 gives us how many oxygen atoms? Well, a half of an oxygen molecule is 1 oxygen atom, right? Then times 25 is 25 oxygen atoms. Do we need that many? Well, let's look over here. 16 oxygens plus 9 is 25. So we did need to do that. Now this equation is technically balanced, but it's not whole numbers. So how do you get rid of that fraction? Remember, if you multiply a fraction by the denominator, it gets rid of the fraction. It leaves you with the numerator. So if we multiply this whole equation through by the denominator, right here, that means 2 of these, 2's cancel here, gives you 25 oxygen, 16 carbon dioxide, and 18 waters. Now we have all whole numbers, and those are the simplest whole number ratio. Just check it out. I mean, can you divide these by a number that will give you another whole number? Well, no, because 25 is odd and the rest of them are even. So there's nothing you can do there. Well, I guess there are situations where you could. Like if you had 6's are even and 9's are odd, you could divide by 3 and reduce that one. But in this case, there's no divisor that will give you a simpler ratio. So that's the answer to this problem, using that intermediate step. Okay, so here we have an unbalanced equation with ammonium phosphate. Right? Check it out and see if it's balanced, right? 3 minus here for this one, 1 plus there for that one. So you need 3 of them. And remember, polyatomic ions, you always have to use parentheses and a subscript if you need more than 1 of them. Plus calcium chloride yields calcium phosphate, right? That's written correctly, and ammonium chloride. Now we need a budget. Right, so here's my budget. So what I've done is set it up with, these are in the initial counts on either side. That should be shifted over a little bit. That red line needs to come underneath the arrow. So I need to work on that slide some. But these are the balancing groups or elements. Notice that ammonium is on both sides, right there and over here. and it has not released its nitrogen on either side. So we know it's intact. We use it as a balancing group. Phosphate similarly did not change from side to side. We use that as a balancing group. Calcium on both sides, chlorine on both sides, and we've accounted for everything for balancing purposes. Now we do an initial count. How many on the reactant side? How many on the product side? So we've got 3 ammoniums, 1 phosphate, 1 calcium, and 2 chlorides on the reactants. We have 1 ammonium, 2 phosphates, 3 calciums, and 1 chloride on the product side. So you can see at a glance that we're not balanced, right? 3 to 1, 1 to 2, 1 to 3, and 2 to 1. That's definitely not balanced. So the question is, where do you start? Well, you don't want to start with something that's already balanced, right? But we don't have that. Sometimes you have balanced situation and you just skip over those. Come back to them later. But I have a tendency to start with the elements rather than the polyatomics. So I would go to calcium first. Say, we got 3 calcium on this side, 1 on that side, so we need to put a 3 in front of this one. Right? So my first step, and that's what this little red 1 is. First step says 3 in front of the calcium chloride, right? Changes the calciums here to 3. Okay? It also changes the chlorides in that first step to 6. Okay? Now we have the calciums balanced at this point, but the chlorides are out of whack. So we'll go to the chlorides. How do you get chlorides balanced? Well, you go over here to ammonium chloride and put a 6 in front of it, right? Because 6 times 1 chlorine yields 6 chlorines. So that's what we're doing here. That gives us 6 ammoniums as well and 6 chlorines, right? So now we've got the calciums and the chlorines balanced. We need to deal with the ammoniums and the phosphates. And unless you see a good reason to change your direction, just go to the next one that you made out of balance, right here. So we'll go to ammonium next. So third step is put a 2 in front of this ammonium. So 2 times 3 means 6 ammoniums. Okay? So that gives us 6 ammoniums, but it changed the phosphates, right? There's only 1 phosphate in that molecule, so 2 times that is just 2 phosphates. And notice, with this budget, we can see at an instant that our equation is balanced. 6, 6, 2, 2, 3, 3, 6, 6. We know it's balanced. If you need, go in and count them up to verify. But we know it's balanced now. And now we can do something with it. You can't do any chemistry with an unbalanced equation. If it's not balanced, all bets are off. It will not accurately describe what happens in a chemical reaction until that equation is balanced. Okay, now how would we express this one? Is this balanced? 1 calcium. There's 1 carbon and 2 carbons here. Acts 3 carbons and 2 oxygens. So we would need to balance it. Right? So if we went to the procedures, we would find that we needed a 2 coefficient in front of calcium oxide, a 5 in front of the carbon, a 2 in front of the calcium carbide, right? That's what this is, and none in front of the carbon dioxide. That would give us the simplest whole number ratio. Now, technically speaking, the ratio would be the same if you said a half here, 1 there, 2.5 there, and 1 there. But that wouldn't be whole numbers. So this is the best answer for that one, correctly balanced. By the way, calcium carbide, if you have any I doubt if your parents, if your father would have used calcium carbide in the mines. They put it in their lamps, right? Put calcium carbide crystals in your lamp, add some water, the reaction releases acetylene gas, and then you light it, and that's your flame. Maybe your grandparent might have used that, but they did away with that because open flames in a coal mine is not a good idea. Okay, so which of the following, checking my time here, which of the following is true concerning balanced chemical equations? Number of molecules is conserved. Is that true? Well, just look at a balanced equation and you'll find that no, the number of molecules is not conserved. We just go back to this one, right? How many molecules on this side? Well, there are 2, consider carbon, 7 on this side, and there are only 3 on this side, right? So that's not false. That's true. False. Not true. False. The coefficients tell you how much of each substance you have. When we interpret that to mean what's the mass, it's wrong. They tell you how many molecules on each side you have, or how many atoms on each side you have, but not how much in terms of mass. Atoms are neither created nor destroyed. That has not changed. Okay. Lavoisier, Dalton, together confirm that this is true. You don't create or destroy matter in a chemical reaction. The coefficients indicate the mass ratios. No, they don't. They indicate the mole ratios of reactants and products. The sum of the coefficients on the reactant side equals the sum of all right, that's just another way of saying 1. Roman numeral 1 and Roman numeral 5 are 2 different flavors of the same falsehood. The only one that's still true is Roman numeral 3. Okay, so if we want to balance, if we're given a word problem, let's see, I'm not scooting around. There we go. If we're given a word problem like this, we're going to heat sodium bicarbonate to produce sodium carbonate, carbon dioxide, and water. So you know what your reactant is. It's just one reactant, sodium bicarbonate. All right, what is bicarbonate? Well, the modern name is sodium hydrogen carbonate. Bicarbonate is a trivial name. It's an antique. And we're going to produce sodium carbonate. That's not written correctly, right? Carbonate is a 2-. And this is only a 1+, so you need 2 of those, right? That's the first place you could make a mistake, not writing the compounds correctly. Carbon dioxide and water also. You know what? I need to move this over. Let's stretch it over here. Sodium bicarbonate plus yields sodium carbonate plus CO2 plus H2O. Okay? So now we have our unbalanced equation written. We need to set up a budget, right? We have actually we have carbonate here and bicarbonate here. So we need to split everything up. We've got sodiums, we've got hydrogens, we've got carbons, and we've got oxygens. Okay. Reactant side, we've got 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygens. On the product side, we have 2 sodiums, right? 2 sodiums. How many hydrogens? 2 hydrogens. Carbons, 1, 2 carbons, and oxygens, 3, 4, 5, 6. Now, what I like to do is once I get my budget tally down is just do a rough count. We got 1, 2, 3, 4, 5, 6 atoms. 1, 2, 3, 4, 5, 6. We've got 2, 3, 6, 7, 8, 9, 10, 11, 12. 2, 4, 6, and 6 is 12. Okay, so I know I haven't missed any. Now, where do we start? Well, we're going to hold, let's start with the most complicated molecule, because any coefficients you add in front of a big molecule is going to change many more atoms than if you put it in front of a small one. So if you don't know where to start, pick the most complicated one, right? So sodium, for these two, I need 2 here, right? So that means 2 there. So that gives me 2 sodiums, 2 hydrogens, 2 carbons, and 6 oxygens. Wow, that was easy. We're balanced. And you can see at a glance that you're balanced. Right? So that is the simplest whole number ratio. Can't reduce it any further for that equation. Now we can do something with it. Right? One of the labs that I use in my general chemistry class is the decomposition of sodium hydrogen carbonate. Did I give that one to you guys too? No, I don't think I did. But we actually use that balanced equation to conduct an experiment. Okay, so if this is balanced, then we should have 4 irons on this side and 4 on that side. Yep, 2 times 2. We had oxygens. 6 oxygens here. 3 times 2 is 6 oxygens there. We're done. That's balanced, and that's what it means. Now, what can we derive from this balanced equation? Well, we can derive a ratio of these two, a ratio of these two, a ratio of these two. So we have 3 conversion factors. Actually, if we flip them, we have 6 conversion factors that are possible out of this one equation. Okay, so if we have 4 moles of iron, produce 2 moles of Fe2O3. There you go. Or 2 moles of Fe2O3 are derived from 4 moles of iron, but each one is equal to 1. It's a unity. That means you can use it as a coefficient, as a conversion factor. So here we have an equation that's probably not balanced, right? 2 oxygens, 3 oxygens on this side. Yeah, that's unbalanced. What are the correct coefficients for that one? Well, I'm going to let you do this one because I don't want to run out of time. You just set up your budget, tally your elements down the left-hand side, just put carbon, hydrogen, oxygen, that's everything. And then add them up for, insert the numbers, initial numbers for the reactant side and the product side, and then go to work with the most complicated one first. And then work your way down. In this case, you'll leave oxygen till last. And if you do that, you're going to end up with 2 moles of C2H6, so we'll have a 2 here. You'll have, well, produces 6 moles of water, but the coefficients are going to be 2, 7, 4, and 6. 2, 7, 4, and 6. This is one where you will use the fraction trick. I can tell you that now. In that process, oxygen will be your last one. And in order to make the oxygens balance, you'll need 7 halves, 7 over 2 as a coefficient. Then you multiply by 2 to get rid of that fraction. And that's why 2 times C2H6 here. Okay. So what do we mean by stoichiometry? Stoichiometry is a fancy word that refers to the Greek for, I forget the actual stoichion, what it means. So I'll just go to the definition. We're using balanced chemical equations to account for masses of reactants and products. So if we know how much reactant is going in, we can predict how much will come out as a product. And you need a balanced equation to do that. But you can't just do it from masses. Right? You have to convert masses to moles before you can move anywhere in an equation. Now, I apologize for this. This exercise is very complicated because it compares two balanced equations. But I'm going to try to make sense of it for you. All right? So we have two equations. One is methane reacts with oxygen to produce carbon dioxide and water. So that's the first balanced equation that's required. Methane plus oxygen yields carbon dioxide and water. So we're going to have to balance that equation first, aren't we? So let's do that. And then once we get it balanced, I can erase all that stuff in the budget and make room for the next one. The ammonia reacts with oxygen to produce nitrogen monoxide in water. So we'll do that one second. So we have carbon, hydrogen, and oxygen. Right? 1 carbon, 4 hydrogens, 2 oxygens. Over here we have 1 carbon, 2 hydrogens, and 3 oxygens. Okay? All right. Carbons are already balanced. So let's go to hydrogens. Right? We need 4 hydrogens over here. So we put a 2 in front of that one. It makes 4. But that makes 2 oxygens plus 2 is 4 oxygens. Correct? Now we need to get 4 oxygens because that one's balanced, that one's balanced. We just need a 2 here, and that makes 4. So that's our balanced equation for the first reaction. Now for the second reaction, we're going to react ammonia and oxygen to produce nitrogen monoxide plus water. Yep, water. Okay, so now we need a budget with nitrogen, hydrogen, and oxygen in it. So we got 1 nitrogen, we have 3 hydrogens, and 2 oxygens. And on the product side, we have 1 nitrogen, we have 2 hydrogens, and we have 2 oxygens. Okay, did I count that right? 3, 4, 5, 6. 5, 6. 2, 4, 5. 1, 2, 3, 4, 5. Okay. The only one that's out of balance is hydrogens. Right? So how do we account for the hydrogens? Well, notice that the hydrogens here, you got a 3 and a 2. And the hydrogens only occur in one place, here on this side and there on that side. So the simplest move here, and this is one hint that I didn't put in the, because I couldn't figure out how to word it. So I figured I'd just leave it for an example. If you got 3 here and 2 here, just say 3 times that and 2 times this. That'll give you the same number of hydrogens. So we say 3 here and 2 here. That gives you 6 hydrogens and 6 hydrogens. But it also changes some other things. Over here it gives you 3, 4 oxygens. And over here it gives you 2 nitrogens, like that. Okay, let's see if I got it right. 2, 6, 8, 9, 10, 8, 10. Okay, that's good. 11, that's 6, 7. Let's see. 6 hydrogens, 3, 4 oxygens. Yeah, 4, 11. 1, 2, 5, 6 is 11. Okay, I'm good. But now we got to balance the nitrogens. So we need a 2 here, right, to make 2. What does that do to the oxygens? Well, it makes 2 plus 3 is 5, correct? So now we need 5 oxygens on this side. How do you get 5 oxygens? Use a fraction. That gives you 5 oxygens. Okay? Now what we don't want to do is get rid of the fraction. So getting rid of the fraction says we multiply by 2, right? To get rid of that 2. So now multiplying by 2 gives us 4 here, 5 here, 4 here, and 6 here. Okay? So now we have 2 balanced equations. Right? And 4, 5, 4, and 6. All right? Those are balanced equations. Now, what do we do with those balanced equations? Well, the question is, we want to know what's the mass of ammonia. Right? That's what it says right there. What mass of ammonia? So many grams of ammonia would be produced when the same amount of water as 1 gram of methane reacts with excess oxygen. So that's a little complicated, but let's work backwards. 1 gram of methane is going to react. Okay, that's what that says. And it's going to produce what? It's going to produce some water, right? So we're going to have, that's the question. Let's say we're going to have X grams of water. Actually, let's say we don't have to do that. X moles of water. Now, why did I say moles instead of grams? Because of the way the question is asked. The same amount of water between these two. So we're going to react this to produce those moles, and then we want the same number of moles here as here. And then work backwards to grams of ammonia. Right? That's why I said it was complicated, trying to tease out what the question is actually asking us for. And that's what it is. So if you react 1 gram of methane to produce this much water, how many grams of ammonia would it take to give you the exact same number of moles of water as in the other reaction? So work this way and then work back. Okay? So here's how you do it. There's a great wall. At each one of these symbols, pluses, arrows, you can't get across that wall unless you have moles. Excuse me just a second here. Okay. So we have to convert this to moles. How many moles of methane is that? Then we can use conversion factor 1 to 2 to find out how many moles of water would be produced. That's where we're headed. Right? So if we want to know moles, right, and we got grams, what does that mean? Grams and moles in a quotient means molar mass. What's the molar mass of methane? Well, we add carbon and we add 4 hydrogens. 16.05. Okay? So we divide 16.05 into 1, which is just a reciprocal, is 6.231 times 10 to the minus 2. 6.231 times 10 to the minus 2 moles of water. Oh, no. Sorry. What am I thinking? Moles of methane. Okay, I'm jumping ahead of myself here. Now convert this number of moles to moles of water. So methane on the bottom, water on the top. What's the ratio? 1 methane, 2 waters. So it's actually 2 times that value. 1.246 times 10 to the minus 1. Right? And the problem says the moles of water need to be equal from here to here. So that's why I wrote it down here, because they're the same. Right? The same amount of water, right there in blue, same amount. So now we can work backwards. We know this many moles of water, so how many moles of ammonia does it take to make that many moles of water? So I'm going to work backwards. What's the ratio? Water to ammonia. Well, 6 waters and 4 ammonias. Right? So 2/3 of this gives us the moles of ammonia. (8.307 times 10 to the minus 2. 8.307 times 10 to the minus 2 moles of ammonia. All right? Almost there. Now we have to convert back to grams. So how do we convert to grams? Well, you need a conversion factor that will get rid of moles. This is on top, right? This is in the numerator. So moles on the bottom, grams on the top. So what's the molar mass of ammonia? Nitrogen is 14.01, and then we have 3 hydrogens, 3.03, right? 3 times 1.01. 1704. So 17.04 times that value is equal to the grams of ammonia. Let's see if I still got it in here. Yep, there it is. So I got 1.42. 1.42 grams of ammonia, right? So we start off with 1 gram of methane. Now, these reactions are not occurring together in the same vessel. These are separate. The connection is theoretical. We want to know the connection here by the water that's produced, right? So this reaction would produce that much water. This reaction with that many grams of ammonia would produce the exact same amount of water. Okay, so that's where these calculations came from. I wanted to do it here step by step so that the calculations that we're doing here would make sense. Okay, 1.42 grams of ammonia. All right, I know that was a big problem to throw at you for your first stoichiometry problem, but hopefully it makes sense. And what you have to do is practice, of course. So go to your homework, practice balancing equations, and then once you feel comfortable balancing equations, work on the stoichiometry. You'll have all during the break, spring break, to become proficient. Now, one other topic, and I got a few more minutes left. I think this is the last one. Yeah, there are several slides, but this is the last topic. And if we have time, we'll do the final concepts that always end on these slide sets. Okay. What do we mean by percent yield? That's what we're getting at. Oh, shoot, down here. There we go. Percent yield right here. That's what we're approaching. We need definitions to get there. Okay, I need to, my board's walking on me again. Okay. Why do we need to know percent yield? What is percent yield? Well, what we've been working with up to this point is the theoretical yield. That is, based on the balanced equation and the amount that you put in, like 1 gram of methane produces so much product water. That amount of water is the theoretical yield. Now, we didn't go all the way to grams, but if we convert that moles of water to grams, that would be the theoretical yield. If you convert all of that methane to water, you should get that amount of water. That's the theoretical yield. The fact of the matter is, when you do that, if you capture the water after that reaction, you'll find that you probably won't have that much. You have something less. That's the actual yield. Now, it's possible to get more than that, get higher than you expect. But if that happens, that means you've got a contaminant in there. You don't have the product. The theoretical yield is the maximum amount of a product that you can obtain from that balanced reaction. The actual yield is what you measure recovered from the actual reaction. You do the reaction, measure how much you get. It will nearly always be less than. Now, why is that? Why would the actual yield be less than the theoretical yield? Well, one possibility is purification. Right? You get, the reaction is taking place in a vessel, and you got to separate the product from everything else, maybe other products, right? And when you do that separation, it's very likely that you'll lose some in the process. So purification will lose some of your product. What's another possibility? Well, let's see. Incomplete reaction. Say you think that 1 gram of methane is going to be completely consumed and end up as product, but maybe it isn't. Maybe the reaction has some reverse component to it. Some of it goes backwards. Then when you purify, you find out that you have less. Right? Third possibility that comes to mind is competing reactions. Competing reactions, or what we often call side reactions. Take your reactants in the wrong direction. They give you some product that's not what you're looking for, okay? Now, the balanced equation won't show those, right? Because they're other reactions, right? They're competing reactions. And that won't give you the product either. So these are 3 possibilities where you would have actual yield be less than theoretical yield. So what you try to do is make the recovery more efficient and reduce the competing reactions. But in the process, you need some way to quantify how efficient your reaction is. And that's where percent yield calculation comes in. Percent yield just means the actual yield divided by the theoretical yield times 100. Now, typically, these are in mass units, like grams per gram. But they could be in mole units, right, depending on the reaction, or volume units if you've got gases reacting. But since it's a percent, you need to know how that percent was calculated. Right? If the percent was calculated using volume, it's going to give you a different value than if it was calculated with mass. So that's why percent is a dangerous unit. In fact, it's not a unit. This is a dimensionless number. It just means parts per 100. So once you know what that is, then you can make some conclusions. We'll try to keep it simple, like mass units would be preferred. So here's an example, right? If the theoretical and the actual yield for this reaction are respectively 5.6 grams theoretical, 4.5 grams actual, calculate the percent yield. Well, obviously, if the actual is less than the theoretical, it's not going to be more than 100%. So A and C can't be it. But you would have to calculate to eliminate D, no correct response. So we do the calculation. Well, we don't show the calculation, but you say 4.5 grams divided by 5.6 grams times 100 equals 80%. Okay? So that means you expect, if you calculate from your equation that you're supposed to get 5.6 grams, you would expect then to only get 4.5 grams. Okay, so we have two concept questions. There are only 5 minutes left. This one references coinage, particularly pennies that were made before 1982. They were actually composed of mostly copper with, I think, a little zinc, 5% zinc. And the reason for the alloy is it strengthens the copper. So, right, if you're going to use pennies every day, people handling and bouncing around in the drawers, banging up against hard surfaces, you want a metal that will stand up to that, but still has basically the intrinsic value of copper. So that's why those pennies were 95% copper. After 1982, the government decided to debase our currency. So it made different forms of coins with less copper because the cost of producing the penny was more than the value of copper. So they put less copper in it and more zinc. In fact, pennies now are copper clad. They have a zinc billet in the center and they're surrounded by a thin layer of copper. And I've got procedures. If you want to recover the copper, you just poke a few holes in your penny and then put it in hydrochloric acid and it'll eat the zinc out and leave the copper. Or if you want the zinc and you don't want the copper, then that takes a little more work. There's a reaction that I've got that'll do that too. But back to the question. These pennies on the average weighed 3.11 grams. How many atoms of copper were present? All right. So what you have to do is say, well, how much copper is actually in this one? It's not 3.11 grams of copper. It's 95% of that. 0.95 times 3.11 gives you the amount of copper. Then you can do the conversion to atoms of copper, right? So there's your conversion. 0.95 grams of copper per 1 gram of penny, or 95% will be 95 grams per 100 grams. Same ratio. Now you convert the grams of copper to moles, right? There's your molar mass. And then you convert the moles to atoms. And there you have the number of atoms in a pre-1982 penny. They did the same thing to silver coinage too. So, and I think it happened in the same year, 1982. So pre-1982 silver coins will be 95% silver. After that, all bets are off. Okay, I got 2 minutes to go. A 2-liter bottle of carbonated soda has an equivalent, on an equivalent average, 0.2 grams of glucose per 100 milliliters. We metabolize glucose in the body from this reaction, which is not balanced. You can tell it's not balanced. Oxygen, oxygen, oxygen. You got 8 oxygens here and only 3 there. Use the following steps in the associated equations to determine the number of grams of CO2 produced after the consumption of 10 2-liter bottles of carbonated soda. right? So that looks like a big problem, but if you break it down, you find that you need the balanced equation, obviously, right? Because you can't tell the relationship between this many grams of glucose and how many grams of carbon dioxide. You need to know that balanced equation, right? So there's the balanced equation. Now, this is what you're given. 2 grams of glucose per 100 mils. But there's a, that's not right. Yeah, that's right. Liters, we're converting milliliters to liters, and then 20 liters, right? 10 2-liter bottles is 20 liters. So now we're converting liters to, we're getting rid of the liters, and that still leaves us with grams of glucose. We're converting to moles of glucose here. Then we're converting moles of glucose to moles of carbon dioxide right here. So this is everything in one calculation, but the steps are there, one at a time. Then we convert back moles of glucose, carbon dioxide to grams. 44 grams per mole is the molar mass of carbon dioxide. So it's all there, but in one single calculation. That's the only way I could get it on one slide. So it turns out with those conditions, you're exhaling 59 grams of carbon dioxide if you drink 10 2-liter bottles of carbonated soda. So look at that, all that global warming. Oh, the pain. All right, we're done. So next Friday, we'll do a review, right, on these 3 chapters that we've covered so far, 4, 5, and 6. Okay?